Welcome to my project bazaar.com. Let me discuss about the process robust blur kernel estimation for license plate images from fast moving vehicles. Let me discuss about the abstract of the project. Analyzing images to estimate the underlying parameters that lead to their formation is fundamentally an inverse problem, since the observed image alone is usually not enough to uniquely determine these parameters. Statistical models are frequently used to choose a likely solution from amongst those that are consistent with this observation. Deblurring is the process of removing blurring artifacts from images, such as blur caused by defocus, aberration, or motion blur. Motion blur is the apparent streaking of rapidly moving objects in a still image. A Gaussian blur is the result of blurring an image by a Gaussian function. A learning-based method of estimating blur kernel under the low L0 regularization sparsity constraint is proposed to sparse representation to greatly benefit kernel estimation and large-scale optimization. The success of recent single image methods partly stems from the use of various sparse priors for either the learned images or motion blur kernels. Apply difference of convex function programming, which is a generic and principled way for solving non-smooth and non-convex optimization problem. Kernel sparse representation is a sparse coding technique in a high-dimensional feature space mapped by an implicit mapping function kernel similarities without the knowledge of the actual form of the kernel. Several pattern analysis and machine learning methods can be tractably solved using kernel methods by choosing appropriate kernel functions that can extract task specific information from the data. The learning problem can be effectively regularized. KSR also finds good kernel matrix approximation to speed up blurring and achieve good deblur performances on digital data. Let me discuss about the flow diagram for our process. Initially, first capture the input image. Here, the license plate image has been taken as an input image from source file by using a getFile and emulate function. User can be able to change the size of the image by providing pixel height and width with the help of imResize function. And this has been done in the image preprocessing block. And select blur image with a specified blur type by choosing the filter type with the help of fspecial and imFilter function. Here Gaussian blur and motion blur is used. The Gaussian blur is a windowed filter of linear class. By its nature is weighted mean. Motion blur is the apparent streaking of rapidly moving objects. And in the angle estimation, the sparse representation has received little attention in parameter interference. The angle estimate is that of for which the maximum of the Readme transform occurs. Naturally, this only works for very long blurs, so that the blurred image is very smooth in the motion blur direction, leading to a clear maximum of the RT. Here coarse angle and also fine angle has been estimated. In this block only the iteration has been initialized. And after estimating the angle, we go for the length estimation. In this length, once the direction of motion has been fixed, we can rotate the blurred image to make this direction horizontal. Then the uniform linear motion blur kernel magnitude of the frequency response on horizontal direction is given. And finally the Fourier transform and Readme transform has been estimated for estimating the length. Core of length estimation is to estimate the distance between two adjacent 0 points of frequency. Then in the deconvolution, without explicit knowledge of the impulse response function used in the convolution, this is usually achieved by making appropriate assumption of the input to estimate the impulse response by analyzing the output. Once the iteration has been incremented, once it reaches the maximum iteration, then we obtain the deblurred resultant of image. If no means we go for again the angle estimation process, and finally we calculated the performance analysis. In this performance analysis we obtain the results of the sparse representation coefficient, so great potential in the angle estimation of linear uniform kernel. A natural extension is to apply to the length interference. Let me discuss about the running procedure for our process. Select the main.m file in the current folder, write the file and run for executing this process. And this is the main window of our robust blur kernel estimation for license plate images from fast moving vehicles. By pressing the read image button, we can browse the image from the dataset folder. Here I am selecting the images and I displayed in the input image axis. By pressing the resize image button, we can perform the resizing process. Here 256 cross 256 is, by selecting the 256 cross 256, the image is resized into 256 cross 256. Selecting the 512 cross 512, image is resized into 512 cross 512, and I displayed in the resized image axis. And by pressing the channel separation button, here we select any one channels. Pressing the red channel button, the red channel is displayed in the axis, and by selecting the green channel, here the green channel of our input image is displayed. By selecting the blue channel, here the blue channel of our input image is selected. And by pressing the blur image button, here any one blur type is chosen. By selecting the Gaussian blur, we can perform the Gaussian blur result. By pressing the motion blur and we can perform the motion blur result, and by pressing the next button we can move on to the next window, and this is the deblurring result window. Here the deblurring, here there are two deblurring operation. For removing the Gaussian blur, selecting the removing Gaussian blur process, we can perform the results, and here I assign the iteration for 10, so this process will repeat for maximum 10 iteration, and each 3 bands are repeated for 10 iteration, so this process will take more time for executing. Nearly it will take 30 minutes for executing. After performing the 10 iteration for our 3 channels, we obtain the results. This is the deblurring results for our Gaussian blur image, and by performing the removal of motion blur, by selecting the removal of motion blur, performing the motion blur removal operation. This will also perform for 10 iteration of our 3 channel, red channel, green channel, blue channel, and this will take also more time for executing. In this red channel initial PSNR we obtain and final PSNR after performing 10 iteration, and mean square error has been obtained. And for green channel also initial PSNR, final PSNR and mean square error. Likewise blue channels also repeated, and in the blur motion blur removing operation, the process will be repeated for 10 iteration of our 3 channels. After performing the 10 iteration of our 3 channels, we obtain the removal of motion blur result, and also the initial PSNR, final PSNR, mean square error for our red channel, green channel and blue channels are obtained. And then by pressing the performance analysis button, we perform the analysis graph of our results. We obtain the various graph and that we analyzed. This is the relation between A and Q theta under different length settings. By varying the angle theta, we obtain the SR score A for various lengths. And here also by varying the angle theta, we obtain the SR score A for our real license plate images. And this is the various SR score A results for our images by adding the Gaussian noise, and this is the relation between the A and theta under different length settings with Gaussian noise for our real license plate images. And this is the RMS result of our by varying the angle. Noise level is set as sigma is equal to 5, and here Lewis metric by varying the angle theta and also by varying the length. And this is the SURE method, SURE method by varying the angle theta and the length. Finally, obtain the SR score by varying the length and also the different curve for various angle theta values. Here we removal of noise of our license plate images have been performed. Thank you.